integration today. So let's talk about kind of some of the weirdness about what it is that we're going to be trying to integrate here, because people, when you think about differentiation and integration as opposite processes, right? So in Calculus 1, let me make sure I'm actually on the camera here. In Calculus 1, when you learn differentiation and integration, you're super self-conscious about that now. You get, oh man, that's really going that time. You get the idea that these are sort of inverse operations, right? That you can start with a function f of x, like sine of x, and then if you differentiate it, so you take d by dx of f, d by dx of sine, you get cosine, and then you can invert that operation. But the fundamental theorem of calculus says that, well, if you invert that operation, cosine of x dx, and you get sine x back again, yeah, you have to pick up an extra plus c because it's an indefinite integral. But ultimately, there's sort of a relationship where basically anything you write down, you can take the derivative of if it's nice enough. And anything you write down, you can integrate. Maybe you can't write down an exact form for the integral. Actually, does anybody remember the sort of functions that don't have formulas? There's a really famous one. Something I can write an integral down, but it actually doesn't. Like if I write an integral with something inside of it where I actually can't write down a function that represents it. We talked about this when we did Taylor series, I think. So the really famous one is e to the minus x squared, or positive x squared. This is the normal distribution from statistics, the bell curve. This has no formula that you can integrate. There's no function that this is equal to. So actually what engineers and scientists do and applied mathematicians is they call this thing ERF, the error function, and it just is the integral of this, and you calculate it numerically. But there's no formula for this. But you can still it's still integrable, even if you can't write down a formula for it. So everything basically can be integrated. So the problem is when you start thinking about what the kind of things you're going to integrate when you come over into multivariate land, it's not even clear what you mean by integration. Right? What's the indefinite integral of a surface? What does that mean? So if I write down something like the double integral of the sine of x and y, I guess there's two variables, so we should think about, there's two variables, I guess, so probably we're going to have to integrate with respect to each of them, and so there's two integrals. What the heck does that mean? Oh, I don't know. Like, what should I do?
Oh, take the derivative with respect to x and then take
The derivative.
Or sorry, the integral with respect to x.
Yeah, okay, that's you.
I told you.
The integral with respect to x, and then the integral. So, like, we're going to just sort of do the opposite of differentiation, I guess is the idea. Okay, so if I isolate this idea, so here's what the suggestion is right now. I should be able to take this thing and calculate its derivative with respect to x. Or I just did it, the integral with respect to x. So the reason this is related to partial derivatives is that you could think of this as a partial integral. There's one way to think about this. Because by extracting this from the inside of another integral, what you've done here is you've assumed that the y's are constant. You've pulled this out. It's like you're fixing a y value, and you're making the assumption that y is not doing anything, and you're just integrating this function like it was a function of x. So you're undoing a partial derivative when you do that. So what's the, if y was a constant here, what would you get for your?
Negative 1 over y cosine x y. Plus c. Wait, no. Oh yeah, plus c.
Plus c is fine. Right? It's going to be a plus c because it's still an indefinite integral. So this is the integration that we already know, but now restricted to the case where it's like a partial integral, because if you took the derivative of this with respect to x, even though it's a function of two variables, the partial derivative of this with respect to x would produce that function. So the dx here is secretly like a partial derivative. Well, then what would you do with that as you proceeded on your journey to recover whatever this integral means, this antiderivative? Take the integral of that thing. So the plus c is important here for a reason that we'll talk about in a second. Okay, so now I'm going to integrate it dy. Oh god, that's good. I picked the worst function in the world. Okay, so then you would proceed probably with some kind of integration by parts or something. Sorry, I picked something I can't actually integrate. Because this is like a product of functions, and there's a y in here and a y out here, and so yeah, my bad for picking a bad example. But the idea is that the structure of what we did here is called an iterated integral. I can do another example where I do it with a polynomial instead, so it's actually solvable. So this is an iterated integral. First, we did it with respect to x, thinking about the inside integral, and then we moved out to the outside to do the outside integral. So maybe I give myself an easier function to work with. Like, how about the integral of x squared plus xy dx dy? So if I did the same game I did before, where I take the inside part and I integrate it, this would be the integral of 1/3 x to the third plus 1/2 x squared y plus c dy, because that is the antiderivative of this, presuming that the y's were constant. This is the regular power rule here. And now I'm going to iterate again with respect to y, and I'll get 1/3 x to the third y plus 1/4 x squared y squared plus cy plus d. Two arbitrary constants in this case when you're finding these antiderivatives. Okay, so the process of solving for an iterated integral in this way is, this is how this goes. We've calculated this antiderivative in this way. Of course, that's just sort of an antiderivative version of this. What if instead I'd asked the other half of the fundamental theorem of calculus? So instead of walking through this thing as an antiderivative question, where I start with a function and I produce something that if I took its partial derivatives, I would get this back again. If instead I asked you something like this, right? What if I took, I don't know, how about a hemisphere? Hemisphere sitting over the xy plane, so something like this. Maybe this is a hemisphere of radius 3. Yep.
Does it matter if it's dx dy or dy dx?
In practice, it can matter, yeah, right? Because what this is telling you is the specific order I asked you to integrate this in. We're actually going to get to a theorem that says when you can switch, right? So there's a theorem that we're going to drive to called, ultimately we're going to get to something called Fubini's theorem, which is a theorem about definite integrals. And that will say generally it doesn't matter what order you do it in, right? Here, the result will matter on the order that you do it in, right? Because if you crawl up dx first and then dy, you're going to get a different thing than if you went dy and then dx. Okay? And we'll talk about kind of like how this goes. There's this technique here where you do indefinite integration is an important part of solving a bunch of equations. I just wanted to present what the indefinite part looked like first, and then we'll start talking about, I'm going to connect this up with definite integrals right now. Because remember, the fundamental theorem of calculus tells us that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a if capital F prime is equal to little f, right? So the indefinite integral is connected to the definite integral by the fundamental theorem of calculus. The area underneath a curve, can be calculated by finding an antiderivative and plugging in the endpoints. So this stuff is kind of like the antiderivative part of what something like a fundamental theorem of calculus would look like. That seems kind of complicated. Let's go over here and look at what the definite integral part of it would look like. So I'm going to write a volume over here, and I'm going to ask, well, the 2D version of area is volume. So a definite integral represents the area under a curve f. I'm going to come over here, and I'm going to write down an expression for the volume underneath a surface. If this is the surface, z is equal to the square root of 9 minus x squared minus y squared, which is what that would be, over the circle. So the domain of this function d is the circle x squared plus y squared is less than or equal to 9. That's the disk that it sits on top of. And I ask the question, hey, what's the volume of that? So the sort of mathematician response is, I don't know what the number is, but I can tell you a symbol that stands for the volume under that surface. The symbol that stands for the volume under that surface is the double integral over the region D of the function f of x and y. And then I'm going to write a quantity called dA, which means a little bit of change of area instead of a little bit of change in length, like over there. So in this case, I would write the double integral over d of the square root of 9 minus x squared minus y squared dA. I have absolutely no idea how to compute that thing. But as a symbol, what it represents is the volume underneath this surface sitting over the top of this region. D looks like this. Sitting over the top of it is a hemisphere, and what that symbol means is the volume underneath that surface. So that symbol, in the same way that abstractly, when we first started doing this, we wrote that symbol down to mean the area under a curve, and then used Riemann sums to justify the symbol. The same way, we're going to write this symbol down to mean the volume underneath the surface, and then we're going to mathematically justify why we use that symbol and give a method for computation as well. Okay. So the easiest possible questions are questions where we work over rectangles. So this is what 15.1 is about. It's integrals over rectangles, double integrals. Over rectangles. And the basic idea of double integration over rectangles is that if I had some kind of rectangle floating in the domain space here, so this is in R2, X, Y, and say this goes from A to B, and this goes from C to D, I can estimate the area of a surface that's sitting over the top of that rectangle by cutting this into little tiny rectangles. So each one of these guys right here, so any one rectangle inside this box, you can think of as being, it has an area described by delta x and delta y. So I can think about delta A, a little tiny bit of area, as being equal to delta x times delta y. So I'm taking my domain, and instead of cutting it up in the, I guess the analogy I'm trying to make here is when we did this in the one variable case, we cut this axis up into little bits of delta x. And then we approximated the function with rectangles with that width. That's how the integral is defined. What we're going to do now is, because the domain is now two-dimensional, instead of cutting it up into little intervals, we're going to cut it up into little rectangles. And instead of doing rectangles for approximating the area under a curve, we're going to do little boxes to approximate volume. So this is the bottom of a box. But we're going to start by noting that in our picture, delta A is equal to delta x delta y. Now if I tip this picture up and I give you a function f, see if I can draw this in the same way. So here's my x-axis and my y-axis. And suppose that you have some surface floating around in space up here. So now I've got some surface. And the surface is sitting over the top of this rectangle I drew right there. So from A to B and C to D. So this is A, B, C, and D. That rectangle there is the same as this rectangle here. And my little delta A that I drew is like this little chunk right there. That's my delta A, my little tiny bit of input area. If I approximate the volume of the surface by making a box that goes up here, and it's just an approximation. Let's see if I got the corners right here. Now the top of this is not going to sit exactly in the surface, right? But if I pick some point inside this little box, so sitting inside that little box is a point that I'm going to call xi, yi, to indicate that I've picked a point in the box. Could be midpoint, could be edge, could be random. There's some point in the box. And then I calculate the height of this thing by calculating, okay, so from here to here is about f of xi, yi tall. So that point right there is the point xi, yi, f of xi, yi. Then I get an expression for a little tiny bit of volume. The volume of this thing that I've drawn, small, so I use my little delta, is going to be equal to the height of it times its base area. So, area of the base times the height gets you volume of a box. So if I was going to approximate the whole surface sitting over the top of this rectangle, whatever it happens to be, so maybe it's this part right here. And what I'm just trying to do is I want to know the volume contained underneath the surface sitting over this domain. I could just add all those boxes up. For every little rectangle down here, I'm going to get a box that comes out that measures an approximation for how far away the surface is. And if I add them all up, I'm going to get the volume of this weird blob that I've drawn. It's not exact, but it's close. So the total volume V should be the sum of all, I'll put an I here, should be the sum of the little volumes. Or if I like, I could write this as the sum of f of xi, yi, delta A. And that's starting to look an awful lot like that integral formula that I wrote down. Another way of writing this down would be, at this point, notice that I could choose to write this as delta x, delta y, or I could choose to write it as f of xi, yi, times delta y, delta x. Delta A doesn't care which order I multiply things in. dx, dy, and dy, dx are the same thing at this stage. So the justification for the formula is, okay, an approximation for the volume underneath that box sitting over this chop job that I've done on the domain. It's like this. Volume is approximately equal to the sum of f of xi, yi, dA. If I let the number of rectangles get very large, that is I can do a finer and finer job of cutting. In the one-dimensional case, you write the sum of xi delta x tends to the integral of f of x dx. As you take a limit, as the number of intervals gets smaller, as the number of intervals get more and the intervals get smaller, you get a better approximation for what the integral has to be. So you're taking a limit as the number of intervals goes to infinity. If you let the number of rectangles go to infinity, you take a limit as the size of the little delta A's goes to 0, and the number of your little delta A sets goes to infinity. Then what comes out is the volume must be equal to the double integral over the rectangle of f of x, y, dA. And that's the justification for using this as our volume formula. It's just a Riemann sum argument. And you can see what's happening here is this is the base of a rectangle, and this is the height, or sorry, the base of a parallel pipe head, and this is the height of it. Volume is equal to area of the base times the height. That's awesome, but it doesn't tell us how on earth we're supposed to compute that. So one thing that we could do is we could just interpret this question as a volume question. So without doing anything else, without doing any computation at all, for example, I could do the double integral over some rectangle R of the function 2 dA, where R is the rectangle where x is stuck between 0 and 2, and y is stuck between 1 and 4. I can do that without doing any sort of calculus at all. Because the picture here is I have a base domain that looks like this. So I go from 0 to 2, and from 1, 2, 3, 4. So I think that rectangle goes like this. That is the rectangle R from 0 to 2, and from 1 to 4. And the surface that sits above it is constantly equal to 2. This sort of question, by the way, shows up in all kinds of exams and like even standardized tests on calculus later. If you ever go to grad school and you got to take the math GRE or even the regular GRE, things like this where you can do it quickly if you understand what's going on versus having to do all the calculus. What I'm giving you then is a box that is at constant height 2 sitting over the top of that rectangle. So R is down here. That's the rectangle R. And the height of that box is constantly equal to 2. So this function, that's the surface. What's the volume? So this is 2 times 3. So the area is 6 on the base. The height is 2. So the volume is 12. So if you don't have a surface like this, where you can easily interpret what's going on as a geometric figure that you can just eyeball what the answer should be, we're going to need some kind of technique to actually solve this thing in general. And so this is our first big theorem. So this is called the iterated integral theorem. Or Fubini's theorem. So Fubini's theorem, which is on page 4, I have to fix the order here, it says the following, that if I have some kind of volume integral written down, the integral over some rectangle, R is a rectangle, of f of x and y dA, so this is just a volume, that I can compute that integral. So here R has x stuck between A and B, and y stuck between C and D, by either integrating the x variable first, and then integrating the y variable, or I can integrate the y variable first and then the x variable. So this is sort of like the fundamental theorem of calculus version of what we're doing in two variables here. What I'm saying is a general volume integral can be computed by replacing the volume integral with iterated integrals. computational trick. And the interpretation of what's going on here is kind of interesting. So mathematically what you do, if we think about this box here, if I integrated the expression I wrote down here using Fubini's theorem would say that the double integral over the rectangle of the function 2dA, which we've already calculated as this box, is equal to the integral from 1 to 4 of the integral from 0 to 2 of 2 dx dy. If you interpret what that means, what this integral is telling you is that for a fixed value of y, so for a fixed value of y, calculate the area of that little slice right there. That's an area, not a volume. This is an area. So what it's telling you is, if you picked out a position y and you calculated the area corresponding to that y, that's what this would be. In this picture, it's like, slice the loaf of bread this way, calculate that area. That is the integral from 0 to 2 of 2 dx. And then multiply it by a little tiny bit of y to get yourself a volume. So it's basically telling you, slice the bread this way. Where this is dy wide. And then add all the bread slices up. If I do the other direction, if instead I had written that this was equal to the integral from 0 to 2 of the integral from 1 to 4 of 2 dy dx, what that would be telling you is, oh no, don't slice the bread that way. Do it this way. Cut your slices up in this direction. The area in that direction is the integral from 1 to 4 of 2 dy. And then you make it a little tiny piece of bread by multiplying it by dx instead. And then what the integral is doing is, I know this is a dumb analogy, but this is a good way for thinking about what Riemann sums are doing, right? When we're working in 2 dimensions, we're slicing bread. The direction that we slice, what Fubini's theorem says, it does not matter what direction you slice a loaf of bread. If you add up the volume of all the slices, no matter how you slice it, you're going to get the same volume in the end. Okay, that's pretty awesome. Essentially, then, we have a technique where I can replace an integral that represents a volume with a convenient choice of the direction of integration. So let me do an example, and then I'll show you an example of when it matters. So a more interesting function might be something like, let's let the rectangle R be equal to, from 0 to 1. Okay, this notation, which you might see in the book, is telling you 0 is less than or equal to x, which is less than 1, and y is less than or equal to 3 and bigger than 1. Right? So this is Cartesian product notation. But it's telling you x comes from this interval and y comes from that interval. And I want to calculate the double integral, the volume over that rectangle of the function x squared plus y squared. I don't see any reason to choose one method over another here. So I'm going to replace this with an integral from 0 to 1, integral from 1 to 3 of x squared plus y squared. And remember that the limits of integration basically tell you which variable you're integrating with respect to first. If I'm integrating with respect to 1 and 3 first, I'm doing a dy integral. And then after I do that, I'm doing a dx. Some authors will actually emphasize the fact that you're doing this in steps by putting parentheses around the interior integral. This is where you're hoping that, like, in this calculus class, all the problems are this easy, I suppose. Because now you're just in the land of calculus you already know. The integral from 0 to 1 of, okay, well, maybe we'll just do this off to the side. So there's a couple of different stylistic choices here. I'm not going to hold you to one or another. To avoid accidentally integrating with respect to the wrong variable or forgetting a symbol or forgetting to do the second integral, a lot of people just like to take the inside integral and do it off to the side. X to the third, x squared, y plus 1/3 of y to the third evaluated from 1 to 3. Remember, in these integrals, the other variable is held constant because these are partial integrals. Okay, so what is this equal to? 3x squared plus y, no, plus 1/3, plus 1 minus x squared plus a third. Isn't it the, 27 divided by 3 is 9, okay. I can do math. Sometimes. I think that's right, yeah? So we get 2x squared plus, oh God, mixed numbers. Okay. 8 2/3. Isn't this 26 over 3? I mean, mixed numbers are awesome, but like they're really hard to work with. So I suggest staying away from in practice. I think that's right. So now we've got this quantity. We've got to bring it back over here so that this integral is equal to the integral from 0 to 1 of 2x squared plus 26 over 3 dx, which again, this is a really basic integral here, but 2/3 of x to the third plus 26 over 3 times x evaluated from 0 to 1, which is 2/3 plus 26/3. Yep.
Did you evaluate both the limits at the end? Like plug in like the y and the x limits?
So no, not when you're doing an iterated integral.
Okay.
Because you remember when we did the indefinite stuff and those extra terms showed up, the c and the d?
Yeah.
You don't want to be carrying those around,
Yeah.
right? Because that's just adding extra complications. So it's just easier to evaluate in the interior first and then proceed from there. It won't change the answer, it's just going to make your life harder to do that.
Yeah.
Okay. So you might think this is the easiest thing in the world, and it is once you get down to the point where you can actually calculate one of these things. I'm going to suggest that sometimes it matters what order you integrate things with respect to. So, for example, let's look at, not that one. Let's look at something like this. Let's look at the double integral from 0 to 1 of 0 to 1 of something like e to the minus x squared dx. Dx, is that what I want to do? Yeah.
You have a problem with x to the dx.
Do I have one? Where is that?
I didn't skip the paper. It's 2.2.
2.2. Oh, that's a good one. Okay. All right. Yeah, we'll look at that one. This is a good one. The integral from 0 to 1 of the integral from 1 to 2 of x e to the x over y dy dx. I don't think you're going to be saved by this one, like in choosing the order that you want to do it in. Do you have a preferred order here?
I started it and I don't know which x.
Ah, so I actually might think to myself, I'm going to deal with the, oh God, there's going to be logs running around. What do you want to do? Do you want to do it this way or the other way? Let's do it both ways. Let's verify Fubini's method by doing it both ways. So this is the integral from 0 to 1 of x e to the x times the natural log of y evaluated from 1 to 2 dx. Which is equal to, okay, log of 1 is 0. So doesn't this turn into the natural log of 2 times the integral from 0 to 1 of x e to the x dx? If I evaluate this function at 2, I get a log 2 times that thing. If I evaluate at 1, I get a 0. So I'm just taking the log 2 outside. Okay? Okay. So now, digging in your pile of technique from the class that I didn't do with you guys. When I see a product of functions inside of an integral, so a reasonable question here might be, how much are we supposed to remember from our integral calculus? And the answer is literally everything, and also everything we taught here too, even if you didn't learn it. How do I do that?
You have to do it.
Integration by
That's integration by parts. So these sort of mixed integrals are very likely to result in functions where you actually have to apply some technique here. So I recognize this as an integral by parts because it's a polynomial times an exponential function. The way that we teach people how to choose, this is a reminder, it's not really a reminder because you guys weren't here to learn this, but the way we teach people how to choose the u and the v, the technique we want to use here is that the integral of u dv is equal to uv minus the integral of v du, integration by parts formula. Or if you want to do it with limits of integration, which a lot of you have not done, remember that you're supposed to evaluate this from a to b as well as this. If you're doing a definite integral and you get things when you're done that are non-numbers, that you've done it incorrectly. So if I'm looking at the integral from 0 to 1 of x e to the x dx, I have to choose what the u and the v happen to be. It's easy in this case because the x will disappear if I take its derivative, so that's what I should choose u to be. We teach a method here called LIPET. So this is for your choice of u. What that means is if you're looking at something that you think you have to do integration by parts on, this is the sort of order of what you really want u to be. If there's a log present, you want to let that to be u. If there's no log, then the next thing you look for is an inverse trig function. If there's no inverse trig function, then you want u to be a polynomial. Then exponential is under that. And then trig function is under that. So this is read from top to bottom, the hierarchy of what you want u to be. There's a polynomial and an exponential, so I'm going to let u be x. Let u be equal to x, dv be equal to e to the x dx. So du is dx, and v is still e to the x. I'm only doing this in this detail because every time we do a new technique that we haven't talked about in a while, I'm going to do an example of it just to remember. So that integral can be replaced with uv, which is x e to the x, evaluated from 0 to 1, minus the integral from 0 to 1 of v du, which is e to the x dx, which gets you, e minus 0 minus e to the x evaluated from 0 to 1. So we got e minus 0 minus e minus 0. This is 0? Yeah. How do I interpret that answer?
The volume is the same above and below the z-axis.
Yeah.
Or the
Volume is also in the same way that when we had area, if I've done this correctly and haven't made an arithmetic mistake, if I integrate something like a sine function on a symmetric interval, the area turns out to be 0 because area is actually a signed quantity when we're thinking about it in terms of integrals, right? There's positive area, which is the area above the x-axis, and negative area, which is the area beneath it. The same thing can happen with volume. The volume sitting above the domain versus the volume sitting below the domain. So if you get a volume of 0 out, it doesn't mean that it's a flat plane sitting on the xy plane. It means that somehow the surface cuts through the axis in a way where there's positive and negative volume and they're canceling each other. At least that's the way I would interpret it. Oh, and then we haven't finished the problem because we have to multiply it by log 2. Sorry. So 0 times the natural log of 2 is still 0. There, now we finished the problem. Did I blow something?
Shouldn't it be?
Oh,
Yeah.
it's 1. Beautiful. Okay, I was worried that I did that. Yeah, e to the 0 is 1, so this answer is 1. So now that integral in here was all, where do we do this? All of that was equal to 1. So all of this is log 2 times 1, which is log 2. Okay. The 0 point still stands, right? If I get 0 out from my volume, it means that I've got a sheet that cuts through and some volume is above the axis and some is, or the plane and some is below. Okay. Let's see if I can find a problem where it matters what direction you do it in. I guess for a rectangle, it's not really going to be that big a deal. What's another good technique that we could employ here? Let's take another example from the notes. Oh man. Okay. Great. Let's look at 2.5, and we'll see if this is double integral of a rectangle 1 plus x squared over 1 plus y squared dA, where our rectangle R is 0 to 2 in the x variable and 0 to 1 in the y variable. You shouldn't get intimidated by these because problems where the functions can be pulled into a function of x times a function of y will always be easy. If they're not blended up together in a composition, I could think of this instead as the double integral over R of the function 1 plus x squared times 1 over 1 plus y squared dA. So no matter what order I do this in, I don't have to worry about x's or y's showing up if I take an integral. I'm basically going to be integrating a function of x all by itself and getting a number, and then integrating a function of y and getting a number. These are the best kind of equations. In fact, this is called a separable function, when you can separate the variables into a product like this. All right, so which way do you want to go? You want to integrate a polynomial or the derivative of an inverse trig function first? Let's do the polynomial first. Okay, so we'll integral from 0 to 2 of 1 plus x squared times 1 over 1 plus y squared dx dy. I know it's dx because I've tagged it with the x. I should probably stick these in here too. All right, so that's the integral from 0 to 1 of x plus x to the third over 3 evaluated from 0 to 2. I should be careful. I'll just put this in here so I'm not being sloppy. I'm trying to show you guys a bunch of different notational conventions you can use to do this. So these, okay, let me be really careful here. When you're doing these, it is good practice to say which variables you are plugging things into. If you're going to write it all in one step like this, instead of separating it off to the side, because there are multiple variables, you are saving yourself if you tag which things are being replaced. So x's are being replaced because this was a dx integral. And that gets you the integral from 0 to 1 of, if you put in a 2, you get 2 plus 8/3. If you put in a 0, you get nothing. So does that make sense? I've just evaluated that polynomial at 0 and 2 and subtracted. Of course now, because you have to remember the things that you've learned in earlier classes, if you're staring down the barrel of an arctangent, you should remember that it's an arctangent. 2 plus 8/3 times the arctangent of y evaluated from 0 to 1, which is 2 plus 8/3 times the arctangent of 1 minus the arctangent of 0. And I know I told you guys that you could leave the arctangent of 1 as the arctangent of 1 if you really want to, but it really makes my brain itch to do that, so I'm not going to be able to help myself. I have to replace this with arctangent of 1. And I would just leave it there. Sometimes I set these problems up so that when you actually compute this, really nice things happen. So it's worth, with the really, really basic trig stuff, just doing it. Okay, that's what double integration on rectangles looks like. It's easy. Except it's easy to the extent to which you remember how to do integrals. So I'm going to write it, like, you don't have to do this one, you don't have to write this one down. I'm going to give you an example of an easy problem over a rectangle. I'll even make it separable if you want. Here, let's write, how about the integral of the integral, and I'll have a natural log of y, and an x times a natural log of x. dx, dy, and I'll just integrate them both from 1 to 2. That looks easy. It's a rectangle, right? Because all you do is you just integrate one variable and the other. I've factored the function, so essentially all I need to be able to do is integrate the natural log of y. And then I should probably also know how to integrate the x times the natural log of x. If I can do both of those things, it's probably trivial. In the sense that you just plug numbers in.
Wait, can you do with u and x everything with l and y make x or
Ah.
Can you make u1 or uln and then
You want to make, just remember the, like,
Okay.
last question. You don't have to write this down. I have Bell hasn't written it, so I still have you guys. If I just wrote this down all by itself, and I said, I would like you to integrate the natural log of y, a technique you're supposed to know.
u is equal to ln.
So yeah, what the LIPAT method would say is, I have no idea, and if I have no idea, I'm going to use integration by parts. This says, let u be equal to a natural log. So I'm going to let u be equal to the natural log of y, and dv just be equal to dy. And then grind through the answer. Somebody last quarter knew the answer to this. What is the antiderivative of the natural log of y? Does anybody know?
It's gonna be like y ln. It's gonna be like y ln y minus
Why?
y.
So that's good. Be able to do that integral. All right. See you guys next time.